Hello, everyone. Hope you stay safe and warm. And my name is Lan. It's my pleasure to host today's graduate seminar in which Dr. Ralph Burden will be giving us a talk on the topic of a new approach in mine tailings disposal using co-disposal to build better dry stacks. Before I invite Ralph I'd like to give a short introduction about Ralph. Ralph is a geotechnical engineer at Frontera Geotechnical Incorporation and recently completed his PhD at the University of Alberta. He has extensive practical experience in international engineering projects and has worked as a geotechnical engineer, specializing in mine waste and Golders Associates in Vancouver, and as an engineer and project manager for an NGO in Uganda. He did his undergraduate and master's at the University of Leeds in England. And during the presentation, I'd like to remind everyone to type your questions in the chat if you have any, and we will address them in the Q&A session after presentation. And with that, I'd like to ask Rolf to come to present. Now the floor is yours, Rolf.
Okay, thanks. So I'm mostly talking about my PhD work today. People often do these presentations as a way to prepare for their defense. I'm bucking the trend a bit by doing it the other way around. So I'd challenge anyone to come up with a question that's harder than what the defense committee came up with. So it's a bit of a background slide. So this slide just shows the way that tailings are traditionally managed. Tailings are most commonly deposited as slurry behind dams. So this slide just shows some sort of typical tailings dams. Some of the potential problems of these are obviously they're risky. The slide on the left shows Mount Polly that I think everyone's familiar with. The other problems with these, they use a lot of water, which in an arid environment can be a problem, and they take a lot of space. Like many larger mines, are simply running out of space to put their tailings. So the slide on the right, at the top right, shows Antamina, which I think is currently the biggest tailings dam in the world. It's about, I think it's almost 300 meters high now. And mines like this are just simply running out of space to put their tailings. So a sort of an alternative approach that people are using more and more is some sort of densified tailings technologies. So these sort of range from slurry, which is a traditional method on the left, through to thickened, and then like sort of the ultimate densified tailings technology on the right is filtered tailings, which where you use a filter like a vacuum or pressure filter to dewater the tailings so it has more of a soil-like properties. And then once you filter it, it can't be pumped. It has to be moved around by conveyors or trucks. This slide shows like the so-called tailings continuum, which just sort of shows it another way. So the slurry end of the spectrum, we have like lower costs, dams are required, higher risk, and more water management to do. And then the higher end, the more filtered end of the spectrum, you have the geotechnically stable. It's easy to create pretty much any kind of landform you want, easy to close, but it's more expensive. This is a common slide that's regularly shown in these sorts of presentations. So this slide shows sort of like I threw this slide in, and it sort of shows the current practice and how typical filtered tailings operations are managed nowadays. So this is a mine in South America, which I think is about 20,000 tons per day, which is about typical for a filtered tailings operation. There's not many really big ones. So I think the biggest filtered tailings operation in the world right now is about 50,000 tons per day. So they haven't really yet managed to scale it up to the really big mines. So this sort of shows typically how they would do it. So they're placing it with trucks, and then they're spreading it and compacting it with normal construction equipment and drying it out for 3 to 5 days and spreading it out in thin lifts. I threw in some more pictures of just how filtered tailings operations currently work. So the top photo shows a stacker, and then the other photos show air drying, compaction, and then placing with trucks. So this is partly why filtered tailings haven't been scaled up to the larger mines yet, because of the amount of work involved in spreading and compacting the material. This slide, this is another, this one hasn't been built yet. This is an older design which has been published. I threw this slide in just to show like how big some of these projects can get, people that aren't familiar with these sorts of things. Like I think if you look at the scale on the right here, this thing is around 200 meters in height. So they're planning on building these pretty big. So this slide just sort of shows what a dry stack might look like. So the focus of PhD was on applying co-disposal to dry stacking. So we talked about what dry stacking is. So this slide is sort of introduction to show what co-disposal is. So really it just means disposing of, so mines typically produce 2 waste streams, usually some kind of waste rock, which in an open pit mine usually get a significant amount of waste rock. And then tailings, which of course are the byproduct from the mill, which are usually finely ground and then deposited as a slurry or thickened or filtered, as we were showing in the slides before. So typically in a normal operation, these materials are disposed of separately. So the waste rock normally piled up in some kind of waste rock dump, and then the tailings will be put in a tailings dam, or they'll be thickened or put in a filtered tailings stack. Co-disposal in general simply refers to the practice of disposing of the 2 waste streams in the same place. There's a variety of ways that this can be done, and this slide sort of summarizes the main ways in order of increased degree of mixing. So some you can stack them in alternate layers or cells, or mix them together and pump them together. But for the purpose of this work, we're talking about the blended co-disposal, where we're actually blending them together to form a mixture. And this is not a new idea entirely. So there was a lot of research was done on this around 2005, 2006, particularly Ben Wickland's research. And that's what these slides show. So a lot of this work showed that if you can mix the materials together in just the right ratio, you can create a blended material. And at that time it was called paste rock. And the idea was that if you can take a waste rock and you fill all the void space with tailings, you can create this engineered material which retains the strength of the rock, and at the same time, because it occupies the void space of the tailings, it can retain the water retention properties of the tailings and the low permeability of the tailings. So this was, at the time, this was not really applied to dry stacking. This was more applied to creating cover systems, or as a way of preventing ARD from acid rock drainage from waste rock dumps. So I've had a few of these projects. When I was working at Golder, I've had a few of these projects come across my desk, and I find they usually get considered, but then they get thrown out pretty quick. And this technique is very rarely applied in practice. And one of the main problems is it's prohibitively expensive to blend the materials, and also you have to have the materials in just the right ratio. It all depends on there being this critical optimum mixed ratio. And usually you don't get that throughout the entire life of the mine. So So that's partly the reason why I think this technique didn't catch on. But there was a lot of research done on it, and my PhD work builds on a lot of this work, as you'll see later on in the presentation. So the focus of the PhD work was on the sort of new concept of blending rock and filtered tailings together. So this has been demonstrated that you can blend it using the same conveyors that you would use to transport the filtered tailings. If you go from one conveyor to the other, then when you through the transfer chute, when the material turns over, you can blend it. So this has been shown, and this has been sort of suggested as a method of enabling filtered tailings dry stacks to be built faster and better. As we showed in the slides before, one of the main problems with filtered tailings dry stacks is the need to spread them out, to dry the tailings off, and then place them in thin lifts. So the hypothesis is by adding rock to the stack and then blending it, we can place them rapidly in high lifts, up to 50 meters in one lift, and build these high stacks and build them rapidly. And that would enable the dry stacking technology to work at really, really big mines, which thus far it's not. The interest in this technology is partly been driven by increases in filtered tailings technology. So now we have these giant filters from the likes of FL Smith and other companies that are producing these. So now we can filter tailings very rapidly in a large scale, but the question becomes, like, can we stack it? And there's surprisingly little research done on the geotechnical properties of these materials. So that was the focus of the PhD research, like how high can we stack this material? What's the pore pressure response when we stack it? What's the shear strength for the material? And then what's the relationship between the properties and the mixed ratio? So how can we control the properties of the mixed ratio of the material by varying the mixed ratio? So what are the potential benefits of adding rock to the stack? So increased shear strength, increased hydraulic conductivity, lower moisture content. It's just keeping it dry. The really important thing with dry stacking is to keep it unsaturated. Once you start to generate positive pore pressures in the stack, you're opening up a lot of problems. You can have undrained shearing, liquefaction. So the really important thing is just to keep it dry, and then that's the way to keep it stable. So that's one of the main advantages of adding the rock to it. Increased density as well, and reduced overall waste volume. So the next part of the presentation, I'll just be going through a couple of sections of the thesis and talking about the research and how it addressed this problem. So the first part of the research was more theoretical based. So going back to the paste rock work and Ben Wickland's work, so he came up with this conceptual model for paste rock blends based on the particle configuration. So it's shown that if you have pure tailings and you add rock to it, first you have a condition where you have rock particles floating in a matrix of tailings, and then if you keep adding rock, then you'll get to a point where you have this like so-called just fill point, optimum mixed ratio. And then if you take tailings away from that, you'll have an unsaturated blend, and eventually you have pure rock. So and then so based on this, you can sort of calculate what the optimum mixed ratio would be, which is a function of the density of the tailings and the porosity of the rock. So we extended this theory to cover the case of filtered tailings waste rock blends. One of the things as well that's in the thesis is the application of ternary diagrams to characterizing these kinds of blends. And so ternary diagrams are quite widely used in the oil sands tailings world. So you can see that the apices of the triangle will be 100% water, 100% rock, and 100% tailing solids. So any blend that consists of combination of water, rock solids, and tailing solids will occupy some space, some point in the middle of the triangle, which can be used as a useful way to quickly characterize a blend, with respect to, because usually the tailing solids content is well known, and so this just provides a quick and easy way to evaluate the potential properties of the blend based on mix ratio. And then the critical point being the transition between rock dominated to fines dominated behavior, which is a function of the porosity of the waste rock skeleton. So this other slide just shows it another way. So here you can kind of see what behavior type you might expect for different types of tailings at different mixed ratios. So this is just supposed to be like a quick and easy tool for high level planning. The other thing we did is we came up with a more extended conceptual model for blends because how this would work when in application is the blends are placed loose from the stacker, and then so the compression behavior of these materials is actually a sort of quite a complex process involving several different mechanisms, and it depends upon, so this is on the mix ratio. So this sort of model attempts to illustrate that, and then you have like different, instead of just the 5 categories, you have more in this case, because we're considering when the material is compacted or uncompacted, and then so we start with a compaction process, and then the stuff eventually becomes saturated, and then you'll have more of a consolidation process afterwards. Then the other section of the PhD we did was more of an experimental. So the next few slides just show the fieldwork component, where we were collecting the materials that we used for the experimental part of the study. So I spent a few months out at Penasquito mine in Mexico, which is it's a fairly big silver and gold mine. And while I was there, we were collecting the waste rock and the tailings that we used for the study. So we were collecting filtered tailings using this like pilot scale filter plant that was set up at the mine. So yeah, I showed up, and then I think I had like about 1 day's overlap with the engineers that set this up, and then I was left on my own to run it. That was an interesting experience. So this is just the whole thing. This is just like a regular filter plant, but in miniature. So it has a whole tailings come in the top into the thickener, and then from the thickener, thickened tailings come out of that and then go into the feed tank, which feeds the filter press. The filter press is shown in the bottom left. All the pressure from the filter comes from the feed pump, which drives it. I think it runs at about 250 psi. The tailings go in there, the plates squeeze together. I think the typical cycle time was around 2 minutes, and then they come out as, they go in about 30% solids and they come out as about 85% solids. And the plates are stacked up vertically. I think I have a video here if it works. This video just shows one cycle of sampling speeded up. So there's the plates squeezing together, and then we're sampling the last one. So the video starts with the end of the cycle, things fall out, they go on a conveyor and then into the thing, and then the next cycle starts automatically. So that's what full-scale filter plant would look like, but this is just much smaller. Oh, I don't know. Yeah. So this slide just shows the waste rock sampling. So we collected the rock from this rock is it's all been crushed already, I think, to about 300 mil minus, and it's been transported by conveyor. Sampling waste rock in general is quite tricky to do because the amount it segregates when it's placed. So we found a spot where they cut into the middle of an existing dump to collect rock for construction purposes, and then we had to collect it from a few different spots and mix it up with the excavator to try to get a representative sample. And then the sample was then scalped in the field to 100 mil before we shipped it off to the U of A, which is what you see in the photos there. So then most of the laboratory stuff was done in Queensland with Professor David Williams. So the main objectives with the program of laboratory tests were to investigate a compression behavior, like how high can we start this? What's the relationship between mix ratio and pore pressure response? And then we also looked at the shear strength. How much does adding rock increase the shear strength? What's the relationship between the mix ratio and shear strength? So this is shear strength section. So the biggest shear box we could find was a 300 by 300. So we scalped the material to 37 mil minus. We did the blending at the U of A, and then we shipped it off to Queensland. We blended it with a concrete mixer. The objective with the blending was just to get it as perfect as possible to generate good quality, repeatable results. We recognized that in real life applications, it won't be blended perfectly, but it's difficult to account for that in an experimental way. So typically when we do these kind of tests, we target perfect blending. And on the slide on the right shows the particle size distributions of the blended materials. So we did 3 different mix ratios, as well as testing rock alone and tailings alone. The 1.8 to 1 is like somewhere around the just filled point from the particle packing theory. So the ratios we tested are well below that. So that is so-called floating condition, where we have a tailings dominated matrix. So there's relatively little research that's been done in the past with blended waste rock and tailings in that kind of ratio, mainly because with the paste rock work, these types of blends simply wouldn't stand up. But with the filtered tailings will stand up on their own, so we can add any amount of rock. So no one really looked at this before. So yeah, we use a 300 by 300 shear box. We use 3 different normal stresses. We use a slow strain rate for fully blended conditions, for fully drained conditions, and tested at the blended moisture content. And those are summary of results. So you can see that there's clearly a significant increase in strength by adding even a small amount of rock to the mix. The other interesting conclusion from this is that at higher stresses, the blended materials were stronger than the rock alone, and we think that possibly one of the possible reasons for that is because the void space is occupied by tailings, which reduces the stress after the class-to-class contact to the rock and prevents the particle breakage that would otherwise occur in the rock. And then the other big piece of experimental work we did was looking at the looking at the compression behavior of the material experimentally. So we developed a whole new test method to do this. So the real important question to answer with this was, how do these materials respond when they're stacking, and what's the pore pressure response? Like generally, stacking dry rock is easy. It has no water in it, but when you start to stack tailings, eventually you get pore pressure generation, which can lead to undrained shearing and liquefaction. So the real important thing with dry stacking is to avoid generating any pore pressure at the base of the stack. As we touched on in the conceptual model slide, this is a really complicated process. It starts with compaction. It's very sensitive to the initial moisture content. It's like a very complex structure. If you look at consider the structure of the material, it consists of sort of lumps of dense filter cake and with large air voids in between, and then large and small rock particles all mixed up. So you can consider this as like a very complicated process. We have compaction, which is leading to unsaturated consolidation, which may possibly also be draining into the air voids, which is eventually leading to a saturated consolidation process. So it's very complex to model, and so we're taking more of an experimental approach to evaluating it, because I don't really know of any numerical model or any theory that could adequately characterize this material. So we took a more of an observational approach by trying to come up with a test method that was repeatable, but would also, as closely as possible, simulate the conditions in the field. And this is what we came up with. So this cell was originally designed for doing large drain consolidation tests on slurry materials and looking at the whole, characterizing tailings for the whole process through from sedimentation through to consolidation. So, but it turns out it worked quite well for this application as well. So it's a 150 mil diameter cell, and has load cells at the top and the bottom, which turns out is very necessary for these sorts of materials. And it has pore pressure sensors, and it's fully computer controlled, so that any combination of load rates and strain rates can be applied to it. The samples are placed in the cell loose, and then the whole process of compaction is followed through from compaction through to unsaturated consolidation through to consolidation at the end. So this slide shows an example of some of the results. So the red line is the vertical stress that was applied to the sample, and the green line is the vertical stress that was measured at the base. The blue line is the pore pressure response. So you'll see that the line has kind of a weird parabolic shape. So we used a continuous rate of loading test to try to simulate the gradual rising of the stack. And we came up with a method to use a incrementally increasing sort of parabolic load rate to simulate the fact that in the field, as the stack rises, the drainage path increases. So when you're considering the process of drainage of pore pressure, the higher the stack gets, which in this case is simulated by a higher vertical stress, then the harder it is for the pore, or the more time it takes for the pore pressure to drain. So we accounted for that by increasing the load rate, increasing the rate of the load as the test progresses. The other thing you'll notice from here is there's a very big difference between the stress that was applied to the sample and the stress that was recorded at the base. So that's why it's so important in this case to use a cell that has a load cell at the bottom. If you're able to get a bigger cell, you can mitigate this as well, because the bigger the ratio between the diameter of the cell and the height of the sample, then the less you'll see this effect. And we were able to use some kind of arching theory to predict this, but in general, I think the best way to manage it is just to is just to account for it by having a load cell at the bottom of the cell. So this shows 3 different materials, and then the slide on the bottom right shows the pore pressure response for the 3 different blends. So you can see that by increasing the rock, you reduce the pore pressure generated in the cell significantly. And this slide. So this slide shows the same data, but based upon the incrementally increasing load rate that we discussed in the other slide, you can kind of, based on this theory, you can calculate what the so-called simulated time would be in field time, and then you will see that then you get the rate of rise becomes linear, representing a linear rate of rise in the stack. So this is the last slide. Yeah, so it's just a bit of a summing up of the conclusions and the contributions of the research. So yeah, it has been demonstrated, I think, that adding waste rock to the filtered tailings stack can help reduce the buildup of pore pressure during stacking and also increase the shear strength. But the real sort of application, the useful application I see is in the development of the slurry consolidometer test. Okay, I see this test as being a relatively quick and easy way to evaluate the stacking performance of all kinds of different blended mine wastes. So it would be a useful way to, you know, if you have like a certain kind of materials, you can try a bunch of different blends and run a whole load of these tests relatively quickly to get an idea about which types of blends and which mix ratios would be the most feasible, and then based upon that data, you could take that away and then scale it up to field trials. So I think I see that as being a useful application of the test. So yeah, I'll leave it there and I'll see if anyone has any questions. It's about half an hour. So.
I've got a couple questions. I don't know.
Sorry, I don't know. I think you have some audience there to ask questions.
We got a bit of a live audience here, so we've got a couple of questions from the audience here, or we can see if there's.
Yeah. Would you mind just repeating their questions in this Zoom meeting so we can know what they're asking?
Yeah, of course, yeah.
Great. Probably can start with mine first, or you want to go first?
No, yeah. You.
Okay. So I will. Anyway, thank you for your great presentation about your PhD work. I have, I think, one question here in the chat. This one is asked by Matt, and he really appreciates your presentation. And he did his master at ASU. I guess it is Colorado State University. Correct me if I'm wrong. On tailings and the waste rock mixtures, and after that came to industry to work as a consultant. He has found something similar to what you have described. Always a solution that is mentioned never worked though. So he knows well there is no one fits all tailing deposition solution, meaning that the solutions are site specific. Oh, I think it's just a statement. It's not an actual question. Oh,
okay.
He follow up some questions in the second part of his chat. He said, in your experience, what are the site specifics? What would work in favor of a tailings and waste rock mixture solution?
What site specifics would work for like what kinds of sites are most suited to this solution? Is this specifically to? I find with the filtered tailings, in general, it seems to be most popular in very arid sites. Just because one of the principal advantages of filtered tailings is that you get the water back. So if you're like in a desert in Mexico or something and you're paying $1 a cube for water, filter tailings becomes very attractive economically compared to slurry. That's not exclusively true. Like, I mean, there's Greens Creek is a filter tailings operation in Alaska in a very wet environment. And so also I see like perhaps in cases where there's very limited space as well, or there just simply isn't somewhere to put a conventional tailings dam, is another case where this is very attractive.
Okay, thank you, Ross. So as we're waiting for other questions, I think probably can just let your audience ask your question.
Okay.
I was wondering, because it was kind of expensive, but when comparing it to like the risks associated with commercial dams, I think it's less likely to fail into that way. Is that considered the cost of like that?
So sorry, I'll try and repeat the question. So the question was, when I said that dry stacks are often considered prohibitively expensive, does that consider the potential cost of cleanup of a potential disaster that might arise from a failure of a tailings dam, or like does it consider the lower risk? And I think that the simple answer is it doesn't. Many mining companies are possibly more short-sighted than they could be in this regard. Yeah, so I think that the simple answer is it doesn't. But you can, I think you can do slurry tailings safely and properly. I don't mean to suggest that you can't, but the dry stacking is just one of several options that is becoming increasingly popular, I'd say, increasingly more likely to be considered anyway.
Okay, thank you. Do you have more questions there, or?
Do we have any more questions in the live audience? No, it doesn't look like it.
Anyway, if not, probably I can ask you a question.
Oh, sorry, we have one more. Sorry.
Oh, good.
Try with different types of rock, different types of tailings, the one mine with the one type.
So the question was, did we try different types of rock and tailings, or was it just one mine and one rock type? And the answer is we only did is one specific mine. Yeah, we didn't try others, but we did develop a method that now anybody can come along and use this method to evaluate any tailings or rock type relatively easily.
Okay, thank you. Let me ask you a question. I think you have done, or you've been planning to do some field tests, and if there's any results, do you think the field measurements would match, like in terms of the population response, or can like be consistent with your experiments results? Is any like comparison between that?
So yeah, I'm not aware of any like large scale trials in this. So the simple answer, I think, is I'd be really interested to see whether or not they match. Yeah, I don't have any data, and I'm not aware of any trials. So that certainly would be the next step. I mean, there has been trials for larger scale trials on blending and on the geochemistry, but I'm not aware of any geotechnical big large scale field trials of this kind of material.
Okay. All right, thank you. I don't think we have any more questions coming up here in the chat. So if that's the case, thank you again, Ralph, for giving us the presentation. And I'd like to conclude this graduate seminar, and I hope to see I thank you everyone to join this presentation too. Hope to see you in the next one. Have a good day.
Thanks.
Thank you, everyone. See you next time. Bye-bye.